Hey, good morning, guys. Discussion today is going to be about the history of seismic waves, or the history of how we got to understanding what these different layers of the Earth were. And there's a short little video that we're going to watch together. It's about 4 or 5 minutes. So, and this will be a fairly quick discussion. So I'm going to present this out here. Okay, so this is kind of where we ended. So, scientists have been able to determine the boundaries, and we looked at this graph, and you had the homework assignment that was based on this graph. But very clearly, we could use this information to help us determine boundaries. We can make some inferences about the chemical composition and those types of things. Okay, the question was how do we get to this point, though? Prior to really the 1900s, we didn't have a very strong understanding of even the causes of earthquakes. Okay. But in the 1900s, our knowledge about earthquakes and the science of seismology really was born. There are 3 scientists that I want to talk about today that made a significant contribution to our understanding, and each one of them kind of helped to put another piece in the puzzle. Okay, so start out with this dude right here. His name was Richard Dixon Oldham. It was 1906. Okay, so he's known for a couple of things. He became the first person that clearly identified that P waves and S waves could travel through the interior of the Earth. Okay, and they could go from one side of the Earth to the other. So when he was studying these waves, if the Earth was one giant continuous layer, as a lot of people thought, if it was just rock the whole way to the very center, then these waves would travel at a definitive speed, and they would land at a definitive place. The problem was that they didn't exactly land where he thought, okay, or they weren't traveling at the same speed. In fact, these waves kind of got to a point where they hit something and then bounced off, so they didn't travel the entire way through the Earth. So he said the only way that's happening is if there's something else that's going on down there. Okay, there's another part there. So we're talking about him today because he clearly was the first person to discover that the Earth actually had a core. Okay, when these waves hit the core, because of how dense it was, we saw a change in their velocity and a change in their direction, and some of them even reverberated back. So that's why we're talking about this guy here, Richard Dixon Oldham. Okay, fast forward a little bit, and this was one of the vocabulary terms. Enter a scientist named Andrija Mohorovičić. Okay, so Andrija Mohorovičić was also studying these waves, seismic waves. What he noticed is that at a very short distance below the surface of the Earth, that the waves actually kind of changed speed and changed direction. Okay, and it was about somewhere around 30 kilometers below the surface, which is the boundary between the crust and the mantle. So he said that so he discovered that there was this transition zone, okay, that it wasn't just that we went to the core, but there was a subtle change here where the waves kind of changed velocity, they changed direction a little bit. And he said that there now, that the Earth isn't made of just 2 layers, a crust and a core, but he actually said that the Earth is made of 3 layers. He said we have a little thin crust, and then all of a sudden the waves change. So there must be then this other continuous, big layer, the mantle, and then we get to the core. Okay, discontinuity, that word, or discontinuous, if you think about that word, it means not continuous, and that's why this is called the Moho discontinuity. It was named in his honor, or it's also called the Mohorovičić discontinuity. But and this is what we said here: waves got faster. We inferred the density and chemical composition must be different, so the Moho was named in his honor. Okay, all right. Enter the last scientist here. Okay, a few years later, 1929, a Danish seismologist, her name was Inger Lehmann. She concluded that there was not just 1 core, but 2 cores. She was looking at seismic data from earthquakes that had happened a few years before, and again, she was looking at and making predictions about when and where these waves should have hit, but it just wasn't matching up. Okay, so she said that the reason is there must be another transition zone. So she became the person accredited with saying that the Earth isn't made of just 1 core, or the core isn't 1 continuous layer, but the core is actually made of 2 parts. So that was named in her honor, and it's called the the Lehman discontinuity. Okay, and that's what we said. So she predicted these P waves could not be deflected by the core, should not be deflected by the core, but they were not. It's called the Lehman discontinuity. Okay, there's a short little clip that I want us to watch here together.
In March 1980, geologists detected a series of small earthquakes here, beneath Mount St. Helens in Washington state. It was a signal that the long-dormant volcano was waking up. Finally, on the morning of May 18th, it did. Mount St. Helens erupted with a force 500 times the atomic bomb that was dropped on Hiroshima. A cloud of hot ash roared 15 miles into the atmosphere. "230 square miles of forest were wiped out. 6 million trees, enough wood to build 300,000 two-story houses." Throughout recorded history, civilization has lived with the threat of earthquakes and volcanoes. But the cause of their destructive power remained elusive, shrouded in mystery. It wasn't until our first great discovery that a picture of what was happening inside the Earth began to emerge. For centuries, most of what we knew about the Earth's interior came from mining operations like this one. It wasn't until scientists began using seismographs to study earthquakes that they gained a more accurate understanding of the inside of the Earth. When an earthquake occurred, seismographs measured the speed and intensity of seismic waves that vibrated underground. Using this method, scientists identified different layers inside the Earth, each one characterized by changes in rock density. For example, the first layer was the crust, a skin of rock covering the planet. Its depth varied from 3 to 30 miles. Below that was the mantle, with a depth of about 1,800 miles. As for what was below that, a breakthrough discovery provided the first clue. In 1906, British geologist Richard Oldham was analyzing seismograph readings caused by a large earthquake when he saw something odd. As the vibrations from the quake reverberated, they did not arrive at the center of the Earth as expected. It was as if they'd hit an obstacle. Oldham realized the obstacle must be the innermost part of the Earth, a dense mass hard enough to have deflected the seismic waves from going all the way through. Oldham had discovered the Earth's core. It was a landmark discovery because it set the stage for the work of another scientist who was about to help revolutionize our understanding of what was happening inside the Earth. With Oldham's discovery, many believed the picture of the Earth's core was complete. But in the early 1930s, Inge Lehmann wasn't so sure. Lehmann was a Danish seismologist who worked extensively in Denmark and Greenland, studying the velocity of seismic waves from earthquakes. In 1936, she was analyzing the seismic waves from an earthquake that had occurred several years earlier. Seismological stations around the world had made recordings of the same quake. By comparing their readings, Lehmann calculated that as the seismic waves had passed through the Earth's core, there was a change in their velocity, as if they had encountered another boundary of some kind. Then it occurred to her. Something was missing from the accepted structure of the Earth's interior. The Earth didn't just have one core, it had two. The core that Lehmann had found was the Earth's inner core. Today, through precise seismic measurements, we know that it's made of solid iron. Solid because gravity at the center of the Earth creates a pressure 3 million times the pressure it exerts on the surface. The core that Richard Oldham had discovered turned out to be the Earth's outer core. It's made of liquid iron and other elements, a hot churning mass that generates electric currents, which in turn create the magnetic field that protects the Earth from dangerous cosmic radiation. Together, the two cores that Oldham and Lehman discovered form a massive structure over 4,000 miles in diameter, slightly larger than the planet Mars. At the center of the core, the temperature can be as high as 13,000 degrees Fahrenheit, which is 2,000 degrees hotter than the surface of the sun.
All right, that's where I want to stop, but I think that video does a good job of tying this together. So, all right, that's the end of the discussion today. Again, hope everything is well. If you have any questions, please make sure that you reach out. Okay, bye.